This is TechSNAP, episode 408, recorded on July 23rd, 2019. Hello, and welcome to TechSNAP, Jupiter Broadcasting Systems, Network, and Administration podcast. My name is Wes, and I'm joined by Jim. Hey, Jim.
What's up, Wes?
Well, we've got lots to talk about today, Jim. That's what's up. I thought, why not start off with one of our favorite things? Yes, that's right. It's some feedback. We got a question into the show from our friend Travis. He writes, Jim, Wes, with all your recent talking up of ZFS, well, I've gotten really interested. We have a handful of old Windows boxes serving various functions at work that we have to VNC into on occasion. Like to move them all off of physical hardware and into VMs. I'm working on repurposing a server to serve as a KVM/QEMU host for those, and I'd like to store the images on a ZFS volume. But as I test this, I've had issues with disk I/O performance on those VMs. If I view the disk I/O in the Windows VM, it'll show 98 or 99% use, but with very low megabits per second. After moving them to an ext partition on another drive, well, they work just fine. Do you have any tips on performance tuning ZFS for KVM images, particularly for VHD files? Love the show, thank you much, and keep up the great work. Well, thank you for your question, Travis. Jim, what are your thoughts?
Oh, so many thoughts. So the first thing is, I don't really have any experience using VHD files with KVM, and I don't know how efficient they are. I've used RAW files, I've used ZVols, and I've used QCOW2 files for the back end. I strongly prefer QCOW2, but if the VHD worked okay on an ext4 partition, that's probably not the source of the issue. That's going to leave a few possibilities. One is that the machine may be under-provisioned in terms of RAM. A good rule of thumb for a VM host with ZFS is you need to have about half of the system RAM available for the system itself and the virtual machines, and the rest of it should be available for the ZFS ARC. If you don't have enough room for ARC, things can slow down pretty badly. Another possibility is that Travis may have 4KN advanced sector format drives, and he may have accidentally created his pool A shift equals 9, which is the setting for 512-bit drives. So check your A shift, make sure it's set to 12 if you got 4K sectors. And there are more tips that you can get into beyond that, but definitely, check your RAM and check your A shift values first. The other stuff usually is not going to have as big of a night and day difference as that.
That's some excellent advice. You mentioned you strongly prefer QCOW as the image format. Do you want to talk just a little bit more about why that is?
Well, so the QCOW2 format actually was created for use with QEMU, which is the full virtualization stack is QEMU/KVM, and QCOW2 was created for use with QEMU to begin with. It's what I began doing serious virtualization on Linux with, and it's never let me down. Some of the features that were originally only available under QCOW2 backend storage have migrated out to other storage formats. Like one of the ones that I'm particularly fond of, if you got a VM that's running on a QCOW2 backend and the host system, not the VM, but the actual host runs out of space on the hard drive, so your thin provisioned virtual machine, then has no ability to write. Well, if you're using a raw volume or file, then generally your virtual machine is just going to crash because it tries to write and it doesn't work and it doesn't know how to handle that. If you're using QCOW2, on the other hand, your VM will actually pause itself. It'll just stop frozen in time, and then you can go in and you can fix your underlying storage problem, delete some files, add disks, whatever, and just resume your paused VM, and it just picks right on up. There's never any actual crash. It just waits for you to fix your issue. I'm not sure if you could do that with VHD file or not. I've been told that that feature is now supported with raw files, where I know it had not always been, because I had some crashes when I had been using raw storage. One other feature is QCOW2 supports virtual machine snapshots, which are a little bit deeper than ZFS snapshots. I don't use these that frequently, but they are a really nice tool to have available in the box. If you do a QEMU snapshot of a virtual machine, you not only snapshot its storage, but also all of its RAM and its system state. So it's basically like hibernating a machine, where you can completely power off the machine. When you turn it back on, it will not. It won't do a traditional operating system boot. It literally just resumes its system state and picks up as though nothing ever happened again. Now, you can use this with virtual machines as a way to migrate them while they're running from host to host, or if you just want to make absolutely certain you're at exactly the place you want to be when you take a snapshot, you have that option. And that's something that you can't do with any other format but QCOW2, as far as I know. I should mention that QEMU and KVM, they support a lot of backing file formats, but they don't necessarily support all of them equally. VMware, for instance, you can import a VMDK file, and you can actually boot a virtual machine directly from that VMDK that you copied in from a VMware host. It will boot, it will run, but I've never tried running long-term on one of those. It's basically just been to make sure that it actually will boot, and I really wouldn't recommend it. I don't think it has the level of testing that something like QCOW2 does.
That makes sense. Thanks for the explanation, and thank you, Travis, for the question. If anyone else would like to send questions our way, well, techsnap.system/contact. Speaking of ZFS, longtime listeners probably remember some unfortunate news in the Linux 5.0 kernel series, which was the dropping of certain kernel symbols used by the ZFS kernel module to accelerate some operations. Well, thankfully, we've got an update.
This is not the first time that we've talked about the SIMD issue with the Linux kernel and ZFS. In episode 396, we brought ZFS on Linux developer Richard Yao on the show to talk about it. The underlying problem is that Linux kernel developer Greg KH decided that he no longer wanted to export symbols to non-GPL kernel modules. And some of those symbols were needed for restoring the state to the rest of the kernel after using SIMD acceleration. The details get pretty technically hairy. You can refer back to 396 if you want to really dig into the nitty-gritty on it. But the upshot of it was none of that stuff actually needed to be done from inside the main kernel. All of the work can be done just as well out in the kernel module that Greg KH didn't want to export that data out to begin with. So it was entirely possible to recreate that functionality in the ZFS on Linux kernel module itself, and that's exactly what Brian Behlendorf and crew have done with the latest patch.
Okay. So they basically determined it'd be safe for them to just re-implement the features that they need to take advantage of the acceleration, not have to rely on the kernel for it, and that's in? Is this in master? Has it shipped anywhere? Are people seeing this good results in the field?
It's in master right now. It's not in any of the release. The most current release is 0.8.1, which is a bug fix release, but does not include the SIMD patch. The SIMD patch will probably hit in 0.8.2. Brian assures me if it's not out in 0.8.2, it will be in 0.8.3. So this should be available in production pretty shortly now, and my typical advice would be, rather than trying to go cowboy and run your file system from master rather than a release, just don't use one of the newer kernels that has the Greg KH "We don't love you anymore" patch in it.
That's good advice. I'll be following myself. I'd seen a recent tweet about ZFS on Linux from Chris Siebenman. You might be familiar. He runs a great blog over at the University of Toronto. And, well, he was having some frustrations with ZFS on Linux, and in particular, dealing with the ARC. I pinged you about it offline, Jim, and when I saw you respond with multiple in-depth paragraphs, I just knew this was show content. I'll read the tweet, and then maybe you can give me your inside tips about what's really going on. One of the frustrating things about operating ZFS on Linux is that the ARC size is critical, but ZFS's auto-tuning of the ARC is opaque and apparently prone to malfunctions, where your ARC will mysteriously shrink and then stick there.
Yeah, whenever we start talking about ARC and memory usage, there's a ton of pitfalls. It's a lot more complex than a lot of people realize. And, also I will say a lot of people don't realize just how well tuned the page cache is in Linux, FreeBSD, and even Windows kernels.
Well, then maybe let's talk about page caches and the ARC. What's going on here? What is the function of these features in file systems and within the operating system?
Okay, so, and every other kind of file system cache boils down to a page cache in your operating system's kernel, whether that be Linux kernel page cache or FreeBSD or, Windows NT kernel. Their file system page caches are they're a simple first in, first out type cache. So you read a block off the hard drive, and now that you've read it, you keep a copy of it in cache. Now, should you need another copy of that block and it's still in cache, you can just service that from cache and avoid having to go to disk. That gets you your result back quicker, and it also leaves more storage bandwidth available for other things that you really do need to hit the metal for. But it's a very naive cache. You can end up evicting pages from cache in several ways. You can either just continue to read data from the drive. Let's say that you set up, like a simple DD command that just reads block after block after block from the hard drive one at a time. Well, once you've read more blocks than you can store in your available memory, you start wiping out the oldest blocks in the cache and replacing them with these newest ones. Which, that sounds great, but what if you've got a block in cache that happens to be part of a critical system library that gets read in all the freaking time from disk? Maybe you've read that block 500 times in the last hour. Should that block get pushed out and replaced with just this one random block from this one process? No, probably not. You should hang on to that one a little while longer. And that's what the ARC does. ARC stands for Adaptive Replacement Cache, and I like to think of it as a weighted cache. Every time you read a block, it gets a little bit heavier. Those heavy blocks, they're really hard to push out, right? Well, the older they hang around, the lighter they get. So it's kind of a battle in between how long has this block been sitting in cache since the last time it was read, and that decides which blocks get evicted from cache first. That means that with the ARC, you can have a much higher cache hit ratio than you do with a simple FIFO cache on busy systems, and it makes her some difficult to benchmark because it really is like a workload focused kind of thing, but in real world workloads, it can make an enormous difference in the actual performance of a machine. For example, rebooting virtual machines is one way that you can really see that in action on a system that's got enough memory to do some caching, but not just an absolutely incredible amount such that you can fit your entire file system in it. What you'll find is that if you reboot a virtual machine whose file system is on ext4, you're mostly reading everything from the hard drive every time because there's just too much of it. It's pushing through RAM. You don't have that many hot blocks left in cache, so there's a lot of drive activity, and it takes a while. You really see the difference when you reboot that same VM from ZFS, and now once you've booted that VM a couple of times, all of those blocks that you need for the boot process, they're in the hot part of the cache. And instead of seeing like a 15 or 20 second boot process, you may be looking at like a 2-second boot process for like a Windows Server VM. It's pretty impressive.
That sounds great.
But that leads us back to Chris's problem. What the ARC is unfortunately not so good at is figuring out when it needs to relinquish memory because something else needs it. Now, the one thing that we didn't cover about that simple page cache that all the operating system kernels have is that anytime an application asks for memory, in the C language, you would say that's the mallocate call. If you go to mallocate a gig of RAM and you don't have a gig of RAM available, but you do actually have, a gig free out of page cache, when the page cache just immediately evicts blocks out of it, the oldest blocks out of it, and hands that over to that mallocate call, and you don't see any kind of an error, it just works. Your page cache automatically shrinks, you get the memory that you asked for, everything's good to go. The ARC, unfortunately, and I'm not really a C developer myself. I haven't tried reading the code and figuring out the hows and the whys, but it's not that good at relinquishing RAM rapidly. Now, it will try to adjust to system pressure. The ARC will grow and shrink according to what's available and what's been requested. But the big difference there is that if you have the exact same scenario I just mentioned, you want to allocate a gig of RAM, and you don't have a gig of RAM free, but you do have plenty of ARC available, your mallocate call will actually just fail. If you keep doing that mallocate, the ARC may eventually shrink and accommodate it, but it's not just going to automatically happen every single time right when you need it, the way that it does with kernel page cache. I found that out the hard way a few times in doing VM hosting on ZFS myself. Now, these days, if you haven't configured it, ZFS will allocate up to half of the available physical RAM for ARC. The ARC isn't always going to be that big, but it's allowed to grow that big if it can and if it wants to. That's without any additional configuration. Now, in the early days of ZFS on Linux, the ARC was allowed to grow much larger than that. And what I would discover is that on a long-running system, if I ever shut down a VM, if I didn't start it back up really, really quick, I wouldn't be able to, because the ARC would have grown into the space that I was normally, allocating to that VM. And so, like I said before, I would try to allocate a few gigs of RAM for that VM. That would fail, and the VM would just refuse to start. That was a really, really annoying problem. And, the only way to get around that, at least at the time, I think you actually can drop the ARC with a syscontrol call now. But back in those days, your only answer is going to be you'd have to just export the pool and re-import it again. And of course, to do that, you'd have to shut down all the other VMs that were on that pool, so that was a problem. As a result of that, I learned to A, make sure that, I did configure my maximum ARC size, and B, configure my VMs intelligently so that I knew that, I'd have enough headroom for RAM for all of my VMs, for the system itself, which doesn't need a whole lot, and for the ARC. Now, these days, part of that work is done for you. For many years now, ZFS on Linux has by default allowed, like I said, half the physical RAM for the ARC. So that part of it's done. That's actually a pretty reasonable value for most systems. And what you want to do then is just make sure, you don't allocate more RAM to VMs than half your physical RAM minus 1 or 2 gigs for the system, and you're good to go.
I mean, that seems like a pretty reasonable and handy rule of thumb.
Now, Chris did also report he's annoyed. He thinks that his ARC is not growing large enough.
Right. He kind of makes the example of like the Linux page cache, right, which many people are used to seeing virtually no free memory on their system. It's all being used for the disk cache. And as you just said, well, the ARC is maybe only using about half.
That's true. This is one of those things we maybe ought to go and fetch ourselves an OpenZFS developer and get them back here on the show to talk about this. I believe that ZFS reads will still end up in the Linux kernel page cache. And I think that part of the reason it doesn't just, grow to monstrous size immediately the way the page cache does is it is looking for those repeated reads before it fills itself. But I'm not 100% sure. I do know that on my VM hosts, I do see the Linux kernel page cache will grow to use all available RAM just as it would on a non-ZFS machine, despite the fact that basically all the storage is ZFS. So that's why I feel fairly certain that it is still in use, and it's probably not as much of a problem that Chris's ARC isn't growing the way he wants it to, because those should, in theory, be mostly ephemeral blocks that are served just fine out of the simpler kernel page cache, and by the time, it's something really hot that really ought to be in the ARC so it can't be evicted so easily, it should be getting there. But a lot of that is guesswork on my part. Maybe let's try to get another developer on the show.
I think that's a great idea. I will say too, it's pretty incredible how well ZFS works on all these systems, as it ends up hooking into the system at a pretty deep level. So I can understand there being some complicated requirements and a little bit of tuning, knowledge, paying attention when you're using something as complicated and amazing as OpenZFS. Well, Jim, if you look at any sort of popular culture, you couldn't help but have seen the recent hubbub about the 50th anniversary of the Apollo 11 mission. And I thought, well, who are we to buck a trend, especially since a lot of the technology involved, well, it's still fascinating.
Wire rope memory.
Yeah, we'll get to that. Now, you've probably heard some of those phrases, things like, your cell phone, it's so much more powerful than any of the machines that were used to take people to the moon and back. And in many ways, that's true, right? If we're just talking about raw computation, all right, definitely. But I think that kind of misses a larger story, which is just how neat and powerful in its own way, capable, you might say, the Apollo guidance computer and a lot of the other technology involved as well really were. And there's a great article over at The Atlantic that points that out perfectly.
I think the best line out of that article, you could not actually guide a spaceship to the moon with a smart doorbell.
Yeah, I couldn't say it any better myself. Now, If you're not familiar, the Apollo guidance computer in the command module had two main jobs. First, it computed the necessary course to the moon, calibrated by astronomical measurements that the astronauts made in flight with a sextant, not unlike how you might actually do it on the ocean.
Or in Ultima 4.
Or in Ultima 4. They'd line up the moon, the Earth, or the sun, and then use the sextant to work out how they needed to adjust their position to hit their target. They fed that information into the guidance computer, and it could then help compute course corrections. It also controlled the many physical components of the spacecraft. The AGC could communicate with 150 different devices within the spacecraft, which is really an enormously complicated task. It had dozens of thrusters, all kinds of interfaces, sensors, and a guidance platform that integrated with the sextant. You start adding all of that stuff up, and it's actually very capable. I think what really strikes me about all this technology is the power of the purpose behind it. You know, a lot of it may not be general purpose, but it just shows the incredible things you can achieve with focus and when you're designing something that just needs to work, right? Especially when you're sending it into outer space.
You know, during a lot of the design phase of this hardware, it was still being programmed with punch cards, but that wasn't going to be practical for the astronauts. They needed a more interactive interface. And they communicated with the computer through something called the DSKY. That's a lot less complex to a modern ear than it sounds. It really was just short for display and keyboard. Now, the crazy thing to me here is that the Atlantic describes this as a user interface system that is not easy to describe, but relies on a series of program codes as well as verb and noun codes. Now, that sounds pretty arcane, but when you look at some examples of the actual commands, it was things like 78 update pre-launch azimuth, all typed out with spaces, or 33 time of ignition for a noun. And I'm looking at this and I'm thinking, go north, get sword, kill troll.
It really does have the feel of a text-based adventure, and it comes from a time when the way we interfaced with computers was just a little bit different.
It's kind of interesting trying to put yourself in, these 60s astronauts' mindsets. Just imagine being in a place in a mindset where you're looking at what amounts to a text adventure interface and thinking, this is the most amazing way to do real-time interaction ever.
And, we really shouldn't sell short the quality of the software, too. There's been a lot of good reporting about Margaret Hamilton, a woman in the very heavily male-biased Apollo program. One thing I couldn't help but notice was they came up with what they called the interpreter. We'd call it virtualization now, and it allowed them to run 5 or up to even 7 virtual machines simultaneously in only 2 kilobytes of memory. It was terribly slow, but it gave them all these features and a nice way to actually reason about how their machine was working.
It's hard to overstate how amazing that sounds, honestly. Several virtual machines running in 2K of RAM. For a point of comparison, in the mid-70s, my dad and I had a TRS-80, affectionately known as Trash 80 Model 1 home computer. The Model 1 came with 4K of RAM, and we had to update it to 8K to be able to run a program called Dancing Demon, which was just Dancing Demon was, again, it was amazing for the mid-70s, years after these NASA missions. And all it really did is just, you had this fully text mode, just high-bit ASCII, blocks of white on the screen, a little demon who would look at you, and you could type in things on the keyboard, and it would start doing little dance steps. You could program little routines and have this little demon figure dancing while your computer went bleep and bop and boop. That wouldn't fit in 4K. We needed 8K for that. And to this day, people who are really in the loop on old computing stuff talk about what an amazing feat it was to cram Dancing Demon into 4 times the RAM that this Apollo mission computer apparently ran 5 to 7 of what, I don't know what these things did, but at least somebody's describing with a straight face as virtual machines.
Amazing. Well, to pair with that fantastic software, there was pretty incredible hardware. Let's talk a little bit more about the guidance computer. It had very little memory by modern standards, of course. 2,048 words of RAM in its erasable core memory, and 36,000 words of ROM, yeah, that's right, read-only memory, in what's known as its core rope memory. Now, you've got to remember here, in the 1960s, most computers used magnetic core memory for RAM. Core ropes, though, they were unusual and operated a bit differently. Erasable core memory and core rope both use magnetic cores, small little magnetizable rings. But while the erasable core memory used one core for each bit, so you had to have a ring and you only got one bit out of that, core rope memory managed to store 192 bits for every single one of those little magnetized rings, achieving a much higher density.
Now, of course, you got a much higher density. You had 192 bits per core instead of a single bit, but you weren't able to actually rewrite any of that memory. It wasn't RAM; it was ROM. Now, you did get 192 times the density in the core rope memory as you would in standard core memory, but the trade-off is that memory was ROM, read-only memory, instead of RAM. You couldn't erase it, you couldn't do anything else with it, because it was actually literally hardwired that way. It's kind of crazy. You actually weaved these ropes, these wires, through the core, either through the core for a 1, or you would bypass the core for a 0. So, once you've made this thing, you can't change it. It's literally been hardwired the way it will always be.
The EGC had 6 of these, 6 core rope modules, each storing 6 kilowords of program information. Now, remember, the AGC, it used a 15-bit word size, which seems funny to us now, but back then wasn't so uncommon. Each module contained 512 cores, each storing 12 words of data. So that is, each module had 192, 12 times 16, sense wires going through or around each core. That can give you a little bit of an idea. Like, this is an incredibly complicated thing, and someone had to actually construct it.
Once a core rope was carefully manufactured using a half-mile of wire, data was permanently stored in the core rope. So I'm going to go out on a limb and guess these things weren't particularly lightweight either.
No, it took like 8 weeks to put it all together and cost about $15,000 per module, all of which meant they had to get the computer code right and frozen months in advance because there's no way you're going to patch that thing on the fly.
I never thought anything would be worse than typing in 15 or 20 pages of code from a magazine when I was a kid, but I think reweaving half a mile of iron wire would definitely take the candle.
Yeah, these stories have definitely given me a new appreciation for all that was accomplished 50 years ago. Of course, we'll have links to everything, techsnap.systems/408. That's enough of the past, though. I thought for our last story in this episode, we could look to the future. I saw you had a fascinating article out over at ours talking about how brains, well, they scale better than CPUs, so Intel is building brains? Jim, what does that mean?
Well, Wes, I do have to admit that, that headline was a little bit sensational. Intel's not really building brains. What they are building is neural tissue. An actual brain has a lot of specific subsystems to it. There's a lot more to it than, just a mass of neurons all wired together. And that's exactly what these Loihi chips and the larger scale Pohoiki Beach hardware that Intel's manufacturing actually are. Traditional computing is basically this incredibly optimized pipeline that you throw a lot of numbers down really rapidly and see what comes out on the other end. The neuromorphic engineering, like what Intel is doing, works like neural tissue in an actual brain, which rather than having this heavily optimized pipeline to get, one big stream of numbers through at a really high rate, you've got massively interconnected, very small computing elements called, neurons in animal brains. And effectively, they are neurons, in the Intel project as well. So rather than this one very high-speed pipeline, you've got a massive neural array. And one of the tasks that these things are really, really good at is pattern recognition, just like what animal and even human brains do.
Right. This sounds like a fundamentally different architecture, and so you can get some incredible results, but does that also mean we're probably not going to be replacing our desktop systems with these anytime soon?
Well, let me ask you, Wes, if you had the chance to absolutely, for free, replace your desktop calculator with a math major from the nearest university, would you?
I think that would depend a lot on that math major's personality.
Well, it's going to be a pretty bad idea either way. You must not know many math majors because they're generally surprisingly bad at arithmetic, which is what the calculator does for you. The point I'm getting at is that that calculator is an example of a simple traditional computing device, and the thing that it does incredibly well. And no matter how smart or well educated or experienced a human is, it's never going to be able to match that calculator in terms of just sheer efficiency and getting the result right every single time. It's a very similar trade off between conventional computing and neural networks. They're just not optimized for the same job.
Right. We're seeing more and more, in phones or even on server motherboards, we're seeing more and more additional computing units, right? And you have your general purpose CPU, but you might have fancy graphics cards or custom ASICs designed for whatever task you're doing. Maybe this architecture could fit there.
Yeah, that's exactly right, Wes. And, we're in the barest infancy of seeing exactly that. Much like our original CPUs, if you're old enough, you might remember that they didn't always have a floating point unit. Floating point processors were originally an add-on chip to your standard CPU, an optional add-on that would greatly accelerate that type of operation. And eventually they got folded into the general chip, and nobody really thinks about the idea of having a processor without a floating point unit anymore. Similarly, eventually we started having graphics processing units. Some CPUs have a built-in GPU now. And in a lot of cases, instead of a GPU built into the CPU, we have an add-on video card, like in a gaming machine. What we're starting to see now is neural processing units coming along with that same kind of concept of this add-on that does another task better than the conventional CPU can, and the two can communicate with one another. Qualcomm is a great example of this. Their new Snapdragon 855 system on chip does include a neural processing unit.
Interesting. So it's not just Intel exploring this technology.
No, not at all. Intel, IBM, Qualcomm, and Samsung are all players in the NPU space. What I thought was really cool about Intel's project is that they're showing really massive gains in efficiency and scale by building this hardware that more closely mimics the design of, what we might think of as real animal brain tissue. Neural networks don't only run on neuromorphically designed hardware. Most of the neural networks today are running either, on IoT gear, or they're running on, GPUs. Much like how you might hash Bitcoin with GPU, you can also run neural networks on GPUs, and they can be considerably faster than conventional processors. But none of this really maps that well to the task of building a neural network. So doing this in software on top of hardware that doesn't work anything like that, it's not very efficient. And what Intel has shown with first the Loihi chip and now with this Pohoiki Beach platform, which really boils down to 64 of these chips all Booyah-based together, it scales a lot further with less overhead and tremendously greater power efficiency than trying to get the same size neural network built on top of conventional computing hardware.
Right. You linked to an example with that Intel's done, right? So these are their numbers. But as they scaled up a network, they were able to maintain stuff in real-time performance. And using comparable IoT hardware, well, it not only used 500% more power, it wasn't even real-time anymore.
And that possibility of scaling faster and further is exactly what I think is exciting about this neuromorphic hardware design. And I think it's going to be crucial. We're expecting more and more out of our artificial intelligence projects. And, our current hardware, if you just compared pure neural capacity from modern neural networks that do the tasks that we expect today, like image recognition and automatic moderation of, social media posts, or automatic moderation of what is or is not porn for a family filter. These things are generally, they're about the neural capacity of, maybe a fruit fly. Eventually, we're going to expect these things to have the kind of capacity that, you would see out of a dog or a human. And in order to do that, we're probably going to need hardware that much more closely mimics the actual brain structure of dogs or humans.
Definitely exciting tech to watch, especially as our uses of this sort of artificial intelligence and neural network powered software increases every day. Well, if, like me, you're going to continue to watch this sort of stuff, well, consider following all of Jim's work over at ours. And for even more Jim, find him on Twitter. He's at
JRSSNet.
I'm there too, at Wes Payne, and the whole network is at Jupiter Signal. If you want to check out some other fine shows, like the excellent Choose Linux with a rebooted crew, exploring all the excitement around discovering Linux, well, go to jupiterbroadcasting.com. We've got them all there. Videos, MP3s, one-stop shop. And of course, check out our live shows. We've got a calendar updated in a time zone near you. Thanks so much for joining us. We'll see you next time.